Let us discuss enthalpy of neutralization. In the enthalpy of neutralization, we will take weak acid versus strong base. Weak acid versus strong base. We will take weak acid. We will take acetic acid. Weak acid we are taking acetic acid. Strong base we are taking sodium hydroxide. Acetic acid reacting with sodium hydroxide to give sodium acetate and water. Enthalpy of neutralization. Enthalpy of neutralization is minus 55.2 kilojoule. Minus 55.2 kilojoule. Okay. Now, why the enthalpy of neutralization is less than strong acid versus strong base? That we will see. This acetic acid is a weak acid. Acetic acid is a weak acid. It undergoes complete ionization by absorbing heat from the surrounding. So it needs what is the energy for dissociation? It needs what is the energy for a complete dissociation? That is 2.1 kilojoule. This acetic acid needs a 2.1 kilojoule for undergoing complete dissociation. Next, sodium hydroxide aqueous. Next, sodium hydroxide aqueous. We will take sodium hydroxide is a strong base. It is in the form of a completely ionized form. It is in the form of completely ionized form. It is not in need of any energy. Then this H plus, this H plus and this OH minus, this H plus and OH minus combines to give water. Combines to give water. During this process, energy is liberated. The amount of energy liberated is minus 57.32 kilojoule. This much amount of energy is liberated. Now we will see the overall reaction. For the overall reaction, we will take this acetic acid in the left side. Acetic acid aqueous we will write. Sodium hydroxide aqueous we are writing. Sodium hydroxide aqueous. Then we will cancel this H plus and this H plus will cancel. This OH minus we are cancelling. Then what is the remaining means sodium and this sodium acetate. And water. Okay, we got a acid base neutralization reaction. For this acid base neutralization reaction, what is the enthalpy of reaction means sum of these two. It is minus, it is plus. That means this H plus combines with OH minus to give water. During this time, energy is liberated. How much means 57.32 kilojoule. When this acetic acid undergoes complete dissociation by absorbing heat, how much heat it absorbs means 2.1 kilojoule it absorbs. Therefore, what is the net amount of heat involved? Net amount of heat involved is minus 55.22 kilojoule. Okay. So enthalpy of neutralization of this weak acid and this strong base is less than 57.32 because acetic acid is weak acid which takes some amount of heat, this much amount of heat for complete dissociation. Sir. Now, if we take different weak acid, how the enthalpy of neutralization will be there? That we'll see. Now we are taking some other weak acid. Some other weak acid, what in the sense HCN, hydrogen cyanide. Hydrogen cyanide is a weak acid. It is dissolved in water. Then sodium hydroxide is dissolved in water. Both solutions are mixed with each other. What is the salt formed means this Na plus and this Cn minus gives a salt NaCN, sodium cyanide, and this H plus and this OH minus combines to give water. For this enthalpy of neutralization is how much in the sense enthalpy of neutralization is minus 12.13 kilojoule. Now see that here HCN is weak acid, here also HCN is, here acetic acid is weak acid. Here sodium hydroxide is strong base, here sodium hydroxide is strong base. That means it is weak acid versus strong base neutralization. It is also weak acid versus strong base neutralization. For this neutralization, enthalpy of neutralization is 55.22. For this neutralization, enthalpy of neutralization is 12.13. Now, enthalpy of neutralization for these two is different, but both are coming under same category, weak acid versus strong base neutralization only. Even then, enthalpy of neutralization is different. Enthalpy of neutralization is different because different weak acid. So this indicates that these two weak acid, how it is there means this weak acid strength is high, therefore it is dissociating easily. This weak acid strength is very low, therefore it is not dissociating easily. For this dissociation, more energy is consumed when compared to this one. For this dissociation, more energy is consumed when compared to this one. Therefore, for this enthalpy of neutralization is much low when compared to this enthalpy of neutralization. Therefore, if we change a different weak acid, if we change the weak acid, if we take different weak acid, then enthalpy of neutralization will be different, because different weak acids will have different extent of dissociation. They require a different amount of energy for complete dissociation. Therefore, enthalpy of neutralization depends on which weak acid we are taking. Okay. Therefore, weak acid versus strong base means enthalpy of neutralization is low when compared to strong acid and strong base set. Next, we will take a HF we will take, and sodium hydroxide we will take. HF and sodium hydroxide we will take. HF is the weak acid. HF is the weak acid. Sodium hydroxide is the strong base. Now, what is the salt formed means NaF is the salt. From this Na plus, from this F minus gives NaF. NaF is the salt and water. Enthalpy of neutralization. Enthalpy of neutralization, how much we will see. Now see, here weak acid is there, it is strong base. Weak acid comes in the sense enthalpy of neutralization is less than 57.32. For which enthalpy of neutralization highest in the sense strong acid versus strong base. For strong acid versus strong base, what is the enthalpy of neutralization means minus 57.32 kilojoule. Here weak acid is there, therefore enthalpy of neutralization is 57.32 less than 57.32. Here also weak acid is there, therefore enthalpy of neutralization is less than 57.32. Suppose if we take strong acid versus weak base, then also enthalpy of neutralization will be less than 57.32. Okay, now we will see here what is the weak acid means HF. HF is the weak acid. In the halogen acids, if we take HF, HCl, HBr, HI, these are halogen acids. In these halogen acids, this HCl, HBr, HI are strong acids. These are strong acids. HF is weak acid. HF is weak acid. Okay. So we have taken weak acid HF and strong base sodium hydroxide we have taken. Now we are taking this for neutralization. What is the enthalpy of neutralization? What is our expectation by from the discussion of these? From the discussion of so far, what is our expectation? Our expectation is what in the sense enthalpy of neutralization for this process is less than 57.32. Sorry, what experiment says that we will see. Experiment says minus 68.55 kilojoule per mole. Experimental result says like this. Enthalpy of neutralization for this process is minus 68. That is even greater than strong acid versus strong base. Though we have taken weak acid, though it is weak acid, enthalpy of neutralization is even greater than strong acid and strong base. What is the reason? What is the reason in the sense from HF what comes in the sense F minus comes. This F minus, how it is there in the sense, this HF if we take, even in gaseous state HF is having hydrogen bond. Even in gaseous state HF is having hydrogen bond. Then liquid state, no doubt, hydrogen bonding. So even in gaseous state hydrogen bonding is there means this F minus is having how much strong affinity with the H plus you see. This F minus is having how much strong hydrogen bonding you see. Therefore, this F minus, in this case, this F minus here, Na plus F minus is there. This F minus in water forms a very strong hydrogen bonding. This F minus in water forms very strong hydrogen bonding. F minus is going for very strong hydration. Hydration as done by F minus is very high. F minus is going for a very high extent of hydration. Hydration in the sense exothermic energy is liberated. F minus is going for a very strong hydration. Therefore, higher amount of energy is liberated. Therefore, enthalpy of neutralization is very high. So, in this case, HF is weak acid. Therefore, enthalpy of neutralization expectation is less than 57.32. But it is how the expectation is there means expectation is wrong. Here experimental result is even greater than strong acid and strong base. For this, what is the reason means F minus is having very high affinity of water. F minus is going for higher extent of hydration. Therefore, hydration in the sense exothermic, therefore more amount of energy is liberated. That's why enthalpy of neutralization is high. Okay. So now we will take weak acid versus weak base. We are taking weak acid versus weak base. We are taking. So what is a weak acid in the sense we will take weak acid is acetic acid we will take, and weak base is ammonium hydroxide we will take. Both are reacting to give salt. Salt is what in the sense ammonium acetate. We are getting a ammonium acetate we are getting, and water. For this what is the enthalpy of neutralization? For this, what is the enthalpy of neutralization in the sense minus 49.36 kilojoule. Minus 49.36 kilojoule. Minus 49.36 kilojoule. So, why the enthalpy of neutralization is less than 57.32 in the sense it is both weak. Acid is weak, base also weak. So, this acid is weak, it undergoes complete ionization by absorbing heat. This acetic acid takes some amount of heat from surrounding to undergo complete dissociation. So, enthalpy of dissociation for acetic acid is how much in the sense 2.1 kilojoule. Then ammonium hydroxide is weak base. It takes some amount of heat from surrounding for undergoing complete ionization, for undergoing complete dissociation. Therefore, enthalpy of dissociation of ammonium hydroxide. Enthalpy of dissociation of ammonium hydroxide is how much in the sense 5.6 kilojoule. 5.6 kilojoule. This H plus and this OH minus combines to give water. Combines to give water. For this case, what is the enthalpy of reaction? What is the amount of heat liberated? That is minus 57.32 kilojoule. So what is the overall reaction? We'll see. Common terms let us cancel. Now acetic acid is there. Acetic acid is the weak acid in the left side. Ammonium hydroxide is a weak base in the left side. Now H plus is getting cancelled. This H plus is getting cancelled. This OH minus is getting cancelled. Now right side we will write ammonium acetate. Right side we are writing ammonium acetate we are writing, and water we are writing. Now we are getting a what is heat involved. What is the amount of heat involved in the sense heat involved is this much. So enthalpy of neutralization of acetic acid versus ammonium hydroxide is minus 49.36. Minus 49.36. Why is it so? In the sense weak acid, acetic acid is absorbing some amount of heat from surrounding. Ammonium hydroxide is absorbing some amount of heat for dissociation. This process, this H plus combines with OH minus, this process liberates 57.32. In this 57.32, ammonium hydroxide absorbs some amount, acetic acid absorbs some amount. Therefore, net is what in the sense 49.36 only. Therefore, enthalpy of neutralization for acetic acid and ammonium hydroxide is 49.36 kilojoule. Okay. So, enthalpy of neutralization for weak acid versus weak base is less than strong acid and strong base. Sir. So, this is about enthalpy of neutralization. Next, we will go for enthalpy of transition. Next, we are going for enthalpy of transition. Now, enthalpy of transition we'll see. Enthalpy of transition in the sense 1 mole of one allotropic form we have to convert into another allotropic form, for which what is the amount of heat involved, that is called the enthalpy of transition. So now we will take 1 mole of graphite. 1 mole of graphite we will take. This graphite we will convert into diamond. This graphite we will convert into diamond. Okay. for which what is the amount of heat involved, that is called enthalpy of transition. That is how much in the sense, that is how much in the sense this much. So enthalpy of transition in the sense 1 mole of one allotropic form should be converted into another allotropic form, for which what is the amount of heat involved, that is called enthalpy of transition. Okay, sir. Next we will see enthalpy of atomization. Now we are seeing enthalpy of atomization. We'll see enthalpy of atomization. So enthalpy of atomization in the sense, take 1 mole of given substance, take 1 mole of given substance and convert that into gaseous atoms, for which what is the amount of heat involved, that is called enthalpy of atomization, we can say. Suppose enthalpy of atomization of N2 gas, it is a given substance. Here what is a given substance means N2 gas, that N2 gas will take. This we have to convert into what? Gaseous atoms. Gaseous atoms. Okay, converted into gaseous atoms. For which what is the energy involved? What is the heat amount of heat involved for this process? That is 43.51 kilojoule per mole. This energy is called enthalpy of atomization of N2 gas. It is called enthalpy of atomization of N2 gas, we can say. Next, enthalpy of atomization of CH4 gas. Okay, here given substance is methane in gaseous state. This we are converting into gaseous atoms, carbon atoms and hydrogen atoms, carbon atoms and hydrogen atoms. For this, what is the enthalpy in the sense? For this, what is the net amount of heat involved in the sense? 1665 kilojoule per mole. 1665 kilojoule per mole. It is called enthalpy of atomization of CH4 gas. Next point is enthalpy of atomization of sodium solid. Enthalpy of atomization of sodium solid. For this, how to write equation in the sense, we are taking sodium solid, we are converting this solid sodium into gaseous sodium. Gaseous sodium. For this, what is the net amount of heat involved? That is 108.4 kilojoule per mole. 108.4 kilojoule per mole. This is called enthalpy of atomization of solid sodium. Enthalpy of atomization of solid sodium. So, now this reaction is also called what in the sense sublimation. Solid is directly converting into gas, therefore sublimation. This is also called enthalpy of sublimation, we can say. This we can say in methane, all the bonds are breaking, therefore it is called average bond energy of methane also, we can say. Here also this nitrogen molecule is converting into nitrogen atoms, therefore it is called bond dissociation energy of nitrogen also, we can say. Sir, now what is bond energy or what is bond dissociation energy, that we will see. Okay, now what is bond dissociation energy? What is bond dissociation energy? We'll see. Okay, bond dissociation energy means for which bond we have to break. Okay, in which case, which bond we have to break, that substance you take in a gaseous state 1 mole. Suppose we want to break bonds in hydrogen molecules, then take hydrogen molecules in gaseous state 1 mole you take. Okay, we want to break bonds in hydrogen molecules, then take hydrogen molecules 1 mole in gaseous state we take. This hydrogen molecules we can write like this. You supply energy and break the bonds here. Then this hydrogen atom is getting separated, this hydrogen also getting separated. These two hydrogen atoms getting separated from this molecule. So that separated atoms we will write like this. It is in gaseous state, it is in gaseous state. To do like this, what is the amount of heat involved? What is the amount of heat involved? We will see. Amount of heat involved is how much in the sense this much kilojoule. This is called bond dissociation energy of hydrogen gas. Bond dissociation energy of hydrogen gas, we can say. This is called what we are saying in the sense bond dissociation energy of hydrogen gas. Okay, so bond dissociation energy in the sense, which substance is given for which we have to break the bond, for which we have to break the bonds, that you take in a gas state. Here we want to break bonds in hydrogen gas, hydrogen molecules. So take hydrogen molecules in gas state. How much we have to take means 1 mole you have to take. Then break the bonds in all the molecules. Then what you have to get in the sense gaseous atoms you have to get. Gaseous atoms you have to get. For this process, what is the amount of heat involved? That is called bond dissociation enthalpy of H2 gas, we can say. Now the given is what in the sense bond dissociation energy of Cl2 is given. So take Cl2, in a gaseous state. Take chlorine molecules in gaseous state. This chlorine molecule we can write it as like this. Break the bonds present in it. Then it is converting into what in the sense gaseous chlorine atoms. Gaseous chlorine atoms. To do the process like this, what is the amount of heat involved? We will see. That is called that amount of heat involved is called what in the sense bond dissociation enthalpy of Cl2 gas. Now see the bond dissociation enthalpy of Cl2 gas and compare with hydrogen. Why hydrogen is having higher value when compared to Cl2? Because in hydrogen 1s orbitals involved in bonding, whereas in chlorine 3p orbitals involved in bonding. Therefore, it is having higher bond dissociation enthalpy when compared to this one set. Okay. Now we will see bond dissociation enthalpy of oxygen. We will see bond dissociation enthalpy of oxygen. Now you take oxygen molecules in gaseous state, 1 mole. This oxygen is having double bond. Break this double bond and convert this into gaseous atoms. Convert this into gaseous atoms, for which what is the amount of heat involved? We will see. That is called that amount of heat is called bond dissociation enthalpy of oxygen gas. So bond dissociation enthalpy of oxygen gas, oxygen, if you want to take oxygen molecules in gaseous state, 1 mole you take and break all the bonds, then get gaseous atoms. Gaseous atoms you get it. For this, what is the amount of heat involved? You see, that is called enthalpy of, that is called bond dissociation enthalpy of oxygen gas. Okay, so this is about bond dissociation enthalpy. Sir, now we took what in the sense diatomic molecules we took. All these are diatomic molecules. Now we will take polyatomic molecule, for which how the bond dissociation enthalpy will be there, that we will see. Polyatomic molecules we will take. Now we will take CH4. CH4 gas we will take. Here this bond dissociation enthalpy we want. So bond dissociation enthalpy of CH4 we want. Sorry. Bond dissociation enthalpy in the sense we have to break the bonds here. Then what we will get in the sense gaseous carbon atoms and gaseous hydrogen atoms we will get. For this process, what is the amount of heat involved? What is the amount of heat involved in the sense 1665 kilojoule per mole? This is the amount of heat involved. Sir. Now we will see this one in a stepwise. We will see first we will take methane. We will take this methane we are taking in the gaseous state. We are breaking the bond here. We are breaking which bond in the sense? Suppose we are breaking this bond. So we are getting what in the sense CH3 we are getting. This cleavage is what cleavage in the sense homolytic cleavage we will take. Therefore, here one dot is there and it is gas and hydrogen gas. Okay, it is also having one dot. Free radicals we got it. Now, what is the amount of heat involved? What is the amount of heat involved? We'll see. Here, amount of heat involved is how much in the sense 427 kilojoule per mole. Okay. Why it is called free radical? Okay, this name is what means CH3 is called methyl. CH3 is called methyl. It is called free radical. We have to call. Why we have to call this is as free radical? Because this carbon is having 3 bonds. 3 bonds in the sense 6 electrons. This is 1 electron. So totally 7 electrons. 7 electrons in the sense odd number of electrons. Odd number of electrons means free radical we have to say. Okay, sir. This bond we are breaking in what way? In the sense in this bond 2 electrons are there. 1 electron we have given to carbon. 1 electron we have given to hydrogen. That means this bond is broken homolytically. Therefore, it is called a homolytic cleavage we can say. This is called what in the sense homolytic cleavage we can say. Then we will take the CH3 dot. This CH3 dot we are taking. This CH3 dot we are taking for a homolytic cleavage. The CH3 dot we are taking for homolytic cleavage. Homolytic cleavage, what we are getting in the sense CH2 two dots we are getting. Now H dot we are getting. It is in gas state. It is in gas state. For this, what is the enthalpy of reaction in the sense 439 kilojoule per mole. 439 kilojoule per mole. Sir. Now here we are breaking CH bond for homolytic cleavage. Here also we are breaking CH bond for homolytic cleavage. Here we have taken CH bond for homolytic cleavage. Here also we have taken CH bond for homolytic cleavage. But what is the amount of heat involved? You see here 427, here 439. Amount of heat involved is different. Why amount of heat involved is different in these two cases? What is the reason? Because here methane, it is a stable molecule. Here methyl free radical, it is not stable. Now here methyl free radical, here methylene diradical. Methylene diradical is there. For this stability is different. This carbon valence is satisfied. This carbon valence is unsatisfied. This carbon valence is unsatisfied. Therefore, the central atom carbon is in different stabilities. Therefore, this CH bond strength, this CH bond strength will be automatically getting different. Therefore, we can say here CH bond dissociation enthalpy, here CH bond dissociation enthalpy is different. So, due to different chemical environment of central atom, the CH bond dissociation enthalpy is getting different. Sorry. Now we will take about this CH2. This CH2 will take. In this CH2, this CH bond we will break. Now we will break a CH bond. This CH bond we will take for homolytic cleavage. So what we are getting in the sense CH tri-radical we are getting and H dot we are getting in gaseous state. For this, what is the enthalpy of what is the net amount of heat involved in the sense 452 kilojoule. 452 kilojoule is the net amount of heat involved. Sorry. Next we will take this CH bond we will take. This CH bond we are taking. Here this bond we are breaking homolytically. This bond we are breaking homolytically. We are getting what in the sense gaseous carbon atom we are getting and gaseous hydrogen atom we are getting. Now what is the enthalpy of this reaction in the sense 347 kilojoule. 347 kilojoule. Now we will see overall. Now we will see overall. Overall, we'll see what are the common terms. We will cancel this CH and this CH will cancel. This CH2, CH2, this CH3, CH3. So left side, what is there? Means CH4 is there left side, and here carbon in gas state and 4 hydrogen atoms in gas state. For this, what is the net amount of heat involved in the sense 1665 kilojoule. Okay. Now, different CH bond is having different dissociation enthalpy. This we cannot remember. Okay, it is for methane itself like this. Like this, hydrocarbons in the sense plenty of hydrocarbons are there. For each compound, one CH bond enthalpy in the sense. For each CH bond, dissociation enthalpy is different in the sense how to remember, how to tabulate it, how to use it. It is impossible. Impossible in the sense much difficult. Therefore, better we can do what in the sense we will take average. We will take here in the CH4 gas we are converting into carbon gas and 4 hydrogen atoms in gaseous state. Means in methane all the four CH bonds we are breaking. All the 4 CH bonds if you break you will get like this. Therefore, to break all the 4 CH bonds, this much energy is required. Means for breaking one CH bond, what is the energy required? Average manner you see. So average manner if you see, that is 1665 by 4. This 1665 is for breaking 4 CH bonds. To break one CH bond average manner, if you see, divide by 4, then you will get a average value. That is how much you are getting, means 416 kilojoule per mole. So this is called what, in the sense average bond dissociation enthalpy of CH bond. This is a average bond dissociation enthalpy of CH bond. Okay, so this is called average bond dissociation enthalpy of CH bond. We can say CH bond average bond enthalpy is this much. It is not actual value, it is average. Okay, therefore for polyatomic molecules we cannot give bond dissociation enthalpy. We can give what, in the sense average bond energy only we can give. Average bond dissociation enthalpy only we can give. Okay, average value only we are giving for polyatomic molecules. Okay, so this is about bond dissociation enthalpy. Next we will see about bond enthalpy. We'll see. Next we are seeing about bond enthalpy. Okay, so now we are seeing about what, in the sense bond enthalpy we are seeing. What is the bond enthalpy? Bond enthalpy is nothing but what is meant by bond enthalpy, in the sense for which bond we want bond enthalpy, means for example we want bond enthalpy of this. We want bond enthalpy of this. We want formation of this bond. Bond enthalpy means formation of this bond. To form this bond, what you have to do means constituent atoms you take in the gaseous state. What is the constituent atoms? Hydrogen atom in gaseous state, hydrogen atom in gaseous state. When bond is forming between these two, what is the amount of heat involved? That is called bond enthalpy. That means you have to make this as 1 mole. Okay. So 1 mole of gaseous, these bonds are forming from gaseous atoms, for which what is the amount of heat involved? That is called bond enthalpy. Okay. So what is bond enthalpy? We know. Now we can say that here reverse of this one is called bond enthalpy. It is called bond dissociation enthalpy. Reverse of this is called bond enthalpy. Therefore, reverse of this means minus 435 kilojoule is the bond enthalpy. So bond enthalpy is exothermic. Bond dissociation enthalpy is endothermic. Dissociation in the sense we are breaking the bond. Okay. Bond enthalpy in the sense bond is forming, bond is producing. Bond is producing, we can say. Sir. Now, let us take one reaction. For that reaction, what is a bond dissociation enthalpy, that we will see. Okay, bond dissociation enthalpy, how we are using that point, we will see. Now, we will take one reaction. For example, we are taking ethanol. With this ethanol, we are taking for combustion. Combustion means it is burning with oxygen. Carbon is taking oxygen to give carbon dioxide, and hydrogen taking oxygen to give water. Okay, let us balance this equation. Here carbon is 2, therefore we will make it as 2. Okay, it is carbon we are making as 2. Hydrogen 5 plus 1, 6. 6 means here 3 we will take it. Oxygen will see, here 2 2s are 4, here 3 1 is 3, 3 plus 4 7, here 1 is there, remaining 6, therefore 3O2. Okay, now we have taken this equation. For this reaction, what is the enthalpy of reaction? We want to find it. For this reaction, we want to find enthalpy of reaction using bond enthalpies. Using bond enthalpies, how to find? Using bond enthalpies, how to find enthalpy of this reaction? Okay, using bond enthalpies, how to find enthalpy of this reaction? We want to know it. So, using bond enthalpies means what we have to do, that we'll see. This ethanol we will take. Ethanol is having 2 carbon atoms, and alcohol means OH group, we can say carbon carbon single bond. 5 hydrogen atoms are there. That 5 hydrogen atoms will distribute like this. Carbon is having valency 4, therefore it will make 4 bonds. Sir, and oxygen we can write O double bond O. How many oxygen? In the sense 3O2, therefore 3O2 we have written. Carbon dioxide we can write like this. How many times? Means 2 times carbon dioxide we have write. Water we can write like this. How many times water we have take? Means 3 times water we have take. Okay. Now first what we have to do means left side is the reactant. Reactant in the sense we have to break the bond. Break this bond. All the bonds we have to break. We have to break all the bonds. Okay. All the bonds we have to break. To break the bonds, energy is required. To break the bond, energy is required. Okay. Therefore, it is endothermic. It is what? Endothermic. Okay. Therefore, to break the bond, energy is required. Okay. So reactants in the sense, we have to break the bonds. Okay, break the bonds. Reactants means we have to break the bonds for which energy is required. Therefore, it is endothermic. Okay, reactants in the sense we have to break the bonds. Okay, so what are the bonds we are breaking? 1 cc bond. Okay, 1 cc bond we are breaking. Okay, 1 cc bond we are breaking. Next, how many CH bonds we are breaking? 1, 2, 3, 4, 5. 5 CH bonds we are breaking. Okay, 5 CH bonds we are breaking. Next, this CO bond we are breaking. CO bond. We are breaking CO bond. Next, we are breaking what bond in the sense? This OH bond we are breaking. Okay. This OH bond we are breaking. OH bond we are breaking. These are the bonds we are breaking in which one in the sense? Ethanol. Okay. Here, which is similar bond? CH bonds. How many CH bonds? 5 CH bonds we are breaking. 5 CH bonds. So, this much amount of energy required for breaking all the bonds in ethanol. Okay. So, so and so amount of energy we have to supply to make ethanol to break all the bonds. Okay. Then this O2 we have to break this bond. How many times? 3 times O2. Okay. So in O2 we have to break the bond. In O2 we have to break the bond. How many times? Means 3 times. So so and so amount of energy we have to supply to break all the bonds in the reactants as per stoichiometric equation. Okay. Then we will see products. In the products, what happens means now all the bonds have been broken. All the bonds broken in the sense, then these atoms all have converted into gaseous atoms. All have converted into gaseous atoms. And another thing we have to remember that we have considered bond enthalpies means this must be in gaseous state. Okay. This must be in what in the sense? Gaseous state. This must be in gaseous state. Bond enthalpies you are using in the sense keep all in gaseous state. Water also keep in gaseous state. Okay, bond enthalpies you are using in the sense take all the things in gaseous state. Take all the things in gaseous state. Okay, because then bond enthalpies means gas only we have to consider. Okay, sir. So all this, all bonds have been broken. So all have converted into gaseous atoms. These gaseous atoms are reorganizing and rearranging. Okay, oxygen, carbon, oxygen, hydrogen, oxygen, hydrogen. Like this, they are arranging. Then bond is forming between these two. Double bond. Here also double bond is forming. Therefore, carbon dioxide is produced. And here bond is produced, therefore water is produced. Okay, therefore here this C double bond O is produced between this carbon and oxygen. Double bond is produced. Okay, so in the product side, in the products, what happens means bond is producing, we can say bond is producing. Bond producing means energy is liberated. Energy is liberated, we can say. Therefore, it is, we can say, exothermic, we can say. This is exothermic. Okay. Therefore, here what bond is produced in the sense between carbon and oxygen, what bond is produced means a double bond is produced. So, between carbon and oxygen, double bond is produced. Like this, how many bonds in the sense? 1, 2, 3, 4. 4 bonds are produced. 4 bonds produced, we can say. Next, we can say here between oxygen and hydrogen bond is produced. Therefore, OH bond is produced. How many OH bond is produced in the sense this is 1 and this is 2. How many times means 3 times. Therefore, 6 bonds are produced. We can say this is the amount of energy liberated. We can say this is the amount of energy absorbed. This is the amount of energy liberated. That difference. That means this is exothermic means minus we have written. This is exothermic, therefore minus we are writing here. It is endothermic means plus. This is exothermic, therefore we have written minus. This is equal to enthalpy of reaction. So enthalpy of reaction is equal to what in the sense sum of the bond enthalpies of reactants, this minus sum of the bond enthalpies of products, we can say. Here minus sign we